before the break, I want to finish up the topic that I call stream algorithms. And thinking about it, I realized I wasn't being too careful, except for, well, there are 4 different algorithms I'm going to talk about, and except for the last one, computing moments. These are algorithms that were all invented before anybody had talked about streams, and yet I somehow think of them as stream algorithms. And I think the reason is that while they were designed to deal with arbitrary sets, if you really have sets, that is, all your data is available anytime you want it, rather than just flowing in as somebody else wants to deliver it, there are always better ways to do things. In particular, these days, you can do a lot in parallel. Okay, so I want to think of these as stream-related algorithms. Although I think you'll see quite obviously that it could just as well apply if you had a large set. Okay, so the first of the topics is the idea of the Bloom filter. Many people, I think, have probably heard of Bloom filters, but let me just introduce the idea briefly. Now, to motivate this, let's imagine I have a web crawler. Now, what's a web crawler? It's a large number of processes, probably running on a large number of machines, and each one is visiting a page, finding the links on that page, reporting the links back to a central server, and you want to make sure that every URL you find eventually gets crawled. Well, not everyone. If you do that, the whole process never ends. But you at least want to have the option of crawling any page that you find. Okay. But you don't want to crawl the same page over and over again. So you'd like to know when one of the crawling processes finds a URL, have I seen it before? Okay. Well, I could do if I had a list of all the pages that I've ever seen, then I could just look it up in some kind of an index. But that's really expensive. So what you'd want, because there are trillions of pages that are being crawled. So what you want is something that takes less space and gives you an approximate answer to the question, have I seen this URL before? So the way you would use a Bloom filter is every time one of the crawling processes reports back a new URL, you're going to hash that in some way, and I'll talk about how that's done, and decide either I've seen it before or I haven't. Okay. Now, if a URL is declared new by this filter, then you will eventually crawl it, or decide not to, because at some point you have to say, I've crawled enough. This is going to be my web index, and anything that's so far out from, so hard to find on the web, I'm not going to report. Anyway, but basically, you sort of want to look at any page that you think is new. Now, the problem with the Bloom filter, again, what you give up in order to save the space is that you sometimes get false positives. Now, in this particular application, things are really not working the right way because you might say that a URL has been seen before when it really hasn't. If you do that, then you're never going to crawl it. Okay. Well, I don't want to spend a lot of time on this, but what you can do is every once in a while you change your Bloom filter. Okay, so now if there's only one link to this page, there's no, it probably has such a low page rank, it's never going to be shown anyway. So you don't worry about it. If there are lots of ways to find it and you occasionally institute a new Bloom filter, you'll eventually, it'll not be a false positive and you'll go look at it. So this is, again, I don't want to spend a lot of time on the example because it's not exactly a perfect example, but it should give you, at least, put things in perspective. It's that the Bloom filter, when it says you've seen something, when it says you haven't seen something, you really haven't seen it. If it says you have seen it, you might not have seen it. And of course, by tuning the filter that it's using more space, you can make it less and less likely that you get a false positive. Okay. Okay. So the Bloom filter, you just think of it as a very long array of bits, and you have one or more hash functions. The hash function will take an element in the stream, let's say like a URL, and it returns a position in the array, presumably equally likely to return any position. Now, you start off with the Bloom filter is all zeros, and when an input arrives, say x, we hash x, and let's say if h is one of the hash functions, we set the bit h of x to 1. Now, it may already have been 1, that's okay, but it will surely be 1 after x arrives. And we do that for every hash function. So let me give you just a little example. In this case, the length of this filter is 11 bits. That's, of course, ridiculously tiny. Think of it as 1 billion bits might be a more appropriate number. We'll assume we have integers. I'm going to have 2 hash functions. The first one is this. You look at the odd position bits from the right end. So the low order bit, since the integer is represented in binary, you're taking the 1's place, the 4's place, the 16's place, and so on, dropping out the other bits, and that gives you some bit sequence which you can then interpret as an integer. And as an integer I, you take I modulo 11, and that's the bit of the array that you want to set to 1. And the second hash function is exactly the same, except it takes the other bits, the even position bits. So, okay, so initially, this is the initial condition. The filter is 11 zeros. Now the number 25 comes in. Now, if you look at it, what I've tried to do is the even position bits are in red and the odd position bits are in black. So if you focus on just say the black, that's what H1 gives you. That's 1, 0, 1. That's 5. 5 modulo 11 is still 5. Now for H2, you look only at the red, and that's 1, 0, that's 2, and again 2 modulo 11 is 2, and therefore you set bits 2 and 5. I'm counting bit 0, of course, is the left end. So I've set those 2 bits to 1s, okay, and the blue bits are the ones that I just set. Now the next stream element, 159, again the black is 0, 1, 1, 1, that's 7, and the even positions are 1, 0, 1, 1, which is 11, and 11 modulo 11 is 0. So I set bits 0 and 7 to 1, so now you can see that 4 bits are set to 1. here's the next stream element. Again, we do the arithmetic. The black gives you 9. The red, wait, sorry, yeah, the black gives you 9. The red is 10010, which is 18. 18 modulo 11 is 7. So bits 9 and 7 get set. Well, 7 was already set to 1, so you don't set it again, or you can, it doesn't matter. And now bit 9 is set. So 5 of the 11 bits wind up being set. Okay? Now, again, the filter is an approximation to the question, have I seen this element before? Okay, so again, a new element comes in. I want to know, or well, is presented to you in some manner. I want to know if I've seen it before. So I compute all the hash functions applied to this new element y. And okay, if all the positions in all the results of all the hash functions are positions that have a 1, then I'm going to say that I've seen y before. Notice we could be wrong. Certainly if I have seen y, all those bits will be set to 1. But it's also possible that they got set, each one got set because of some other input that happened to hash to that position. Again, we could have false positives. We say that we've seen it, but we haven't. But on the other hand, if any one of the positions is 0, then we surely haven't seen y, because if we had seen y, we would have set that to 1. Okay. So here's a, again, this was the Bloom filter as I left it after those three inputs came in. And now I want to know, is 118 a member of the set? Obviously it wasn't. If you remember, 118 was not one of the elements that came in. So I break 118 binary is that, so it's 1110 is H1, so that's 14 modulo 11 gives you 3. So H1 of y is 3, and H2 of y, that's the red, is just 5. Now it turns out bit 5, which is of course the 6th position in it's 0, 1, 2, 3, 4, 5. The 5th position is 1, so it looks like maybe we did see 118. But fortunately, position 3, 0, 1, 2, 3, is a 0. So I'm absolutely certain that I have not seen 118. Okay, now, you want to know certain things. In particular, you want to know what's the false positive rate. Okay. Well, the only way you can get a false positive is if at random you have set all the bits that are the targets of each of the hash functions. You've set them to 1. So I'm saying the probability that a given element is a false positive is the fraction of the array that's 1s raised to the power of the number of hash functions, because we assume the hash functions are independent. So you've got that number of independent events, each of which occurs with the probability that is the fraction of the 1s. Okay. Now the number of 1s will be roughly the number of elements you've inserted times the number of hash functions you're using. But it's going to be a little bit less than that. Why? Because there'll be some collision. Sometimes you'll be setting a bit to 1 that already was 1. And we can actually do the math. I want to do the math because it comes up in a number of guises, and I don't want to have to do it all. Do it each time. I'm just going to sort of throw it out from here on. But okay, think of it this: you have d darts. D is the number of elements times the number of hash functions, and you've got t targets. T is the length of the array. Every dart gets thrown, hits one of the targets. Again, it's all random, equal probability. And what I want to know is what's the expected number of targets that are hit by one or more darts? Okay, so let's see. Okay, the probability, if I throw one dart, the probability that any given target is hit is 1 over t, the number of different targets. Now, I claim the probability that I throw d darts and a particular target is not hit is this. It's 1 minus 1 over t. Well, that's the probability that one dart doesn't hit it. And again, because the darts are independent events, I raise that to the number of darts that I throw, and that gives me the probability that a target is not hit, or put it another way, that it's 0 in the bit array stays 0. Now, I want to write this as well as I've done here. All I've done is I've replaced d by t times d divided by t. That's still d, obviously. But notice what I have, which is 1 minus 1 over t to the tth power. So that's like 1 minus epsilon to the 1 over epsilon. And as epsilon goes to 0, what is that? 1 over e. Right. Okay, well, okay, so, again, so all right, if I take out everything but the d over t, that's 1 over e, or e to the minus 1, and then I've got that raised to the d over t power, so you get e to the d over to the minus d over t. Is the probability that an element of the array stays 0. Okay, so let's say do the math. Okay, suppose I'm going to have an array, my size is 1 billion, and I'm going to use 5 hash functions, and I'm going to insert 100 million elements. Okay, so how many darts do I have? Well, 500 million darts, 1 billion targets. So what is the probability that a target is never hit? Well, that's probability is e to the minus a half, and if you look it up in a table or something, it's about 61%. So 39% of the targets do get hit, 61% do not get hit. Okay, that's sort of, it should be like 50% hit, 50% not hit, but again, because some targets going to have 2 darts or 3 darts sticking out of them, the actual number of targets that remain clean will be a little over half. Okay. So anyway, the density of ones is the complement of that. That's 0.393, and therefore the probability of a false positive. Remember, we have 5 hash functions, so it's 0.393 to the 5th power, and it's a little bit under 1%. Okay. So if I want to look up an element, 1% of the time when it is not present, I will say falsely that it is. But that's all it is, just 1%. Okay, let's see. Moving right along here. Okay, I want to talk about sampling a stream. The idea is sometimes you can't afford to process an entire stream, but you'd like to answer a question by looking at only a sample of it. This is a very common problem. Again, and it's also a problem in databases. You have some humongous set, and you could process the whole thing, but if you take a random sample, very often you can get the right answer. But what I want to show you is you got to do it right. Okay, so here's an example of a stream type of problem, and so Google wants to look at all the search queries that have been asked for the past month and find out how many of these have only been asked once. That is, they appear in the stream, but they don't appear. But they only appear once. Now, again, you could process the whole stream because this, the obvious algorithm is going to require you to then record everything you've ever seen, and sort of count how many times it appears, or at least count it's appeared once, it's appeared more than once. Once it's appeared more than once, you don't care about it. But you can't forget about it, because if it then appears again, you don't want to think that that's the first time it appeared. So it's a little messy. So let's say we'll sample 1/10 of the stream, and then we'll just multiply the answer by 10. Okay, does that work? No. Okay. The trouble is that the fraction of queries that are unique in the sample is not going to be the same as the fraction that appear in the whole stream. So you can't just multiply it by 10. And in fact, it turns out that there's no number you can multiply by to adjust the answer in the sample to give you the true, or an approximation to the true answer in the entire set. This is just a completely wrong way to do things. But I want to just explain, I think, one more slide to explain why. Obviously, we're taking at random a sample of 10% of the stream. If the query is unique, then it has a 10% chance of being in that sample, and will surely be unique in that sample, so it'll be identified. But suppose the query occurs twice in the stream. Well, I claim it has an 18% chance of appearing exactly once in the sample. Okay, because you got first occurrence, second occurrence. Chance of the first occurrence appears is 10%. And if it does appear, the chances are 90% that the other one will not appear, and therefore will make the first occurrence look unique. So that's 9% of the time. And then the same way, 90% of the time, the first occurrence won't appear, but the second one will, 10% of the time. So that's another 9%. That's why I get 18%. If it appears 3 times, there's a 27% chance it'll be unique or something. At any rate, the point is, since you don't know the distribution of a number of occurrences, you don't know how many unique things you're going to falsely see in the stream. And the bottom line is this is just not the way to do it. Okay, so then the interesting thing is there a way to do this? Can I actually sample 10% of the stream and get a number which will be the fraction of stream elements, so the fraction of sample elements that are unique will tell me the fraction of elements that are unique in the entire set? Is it even possible? How many think yes? Yeah, I obviously wouldn't be doing this if the answer were yes. Right? But you got to do it right. Okay, and the answer is that, okay, what was going wrong was we were sampling based on the position in the stream. So we're just looking at the stream but taking this position, that position, and so on at random. What you want to do is sample values. But you don't know what values are. You don't know what all the search queries are going to be in a month. So this is another application of hashing. Okay. So, for example, suppose I take a search query, just hash it to 10 buckets. Okay. Again, so at random, the probability, of being in any bucket is 10%. And my sample will be all those search queries that happen to go to bucket 0. Now, the nice thing about this is, if you look at a search query, porn, let's say, it will either be in bucket 0 or it won't. If it's in bucket 0, all of its occurrences are in the sample. So if it's unique in the sample, it will be unique in the full set. Okay. If it's not in bucket 0, none of its occurrences will be in bucket 0. You'll never even see it in the sample. Okay. And therefore, the fraction of unique occurrences in the sample should be a good estimator of the number in the entire set. Fraction, it should be the same fraction. Well, just sort of do some icing on the cake here. That's fine as long as I say, well, I want a 10% sample. If I wanted a 5% sample, I'd hash the 20 buckets. Okay, but what if I don't know how long my stream is going to be, and I don't know how many search queries are going to be asked in a month, but I want my sample size, let's say, to be no more than 1 billion search queries, no matter whether that's a 10% sample or a 2% sample or what. Well, you don't have to hash to only if you want a 1 in k sample, you don't have to hash to just k buckets. You can hash to many buckets. And, I think the example should make it clear. So we'd like a 10% sample, but we also can't, as the stream comes in, if that sample gets too large, we might want a smaller sample. Okay. Then let's say I hash to 100 buckets. Well, again, I want a 10% sample, so I'll take buckets 0 through 9. Or I could pick any 10 buckets I liked, but let's just say 0 through 9 to be concrete. Now, suppose the sample is too big at some point. So now I'm saying, oh, gee, I really shouldn't have taken all 10 of those buckets. Let me get rid of one of the buckets, say bucket 9. Well, I can do that because I can rehash everything in my sample, or I can keep the hash value along with every sample element that I've taken. And I simply throw out of the sample everything that hashes to bucket 9. And I maintain this idea that I'm only keeping an element in my sample if I keep all elements in my sample, all identical occurrences of that element in the sample. Well, anyway, if I need to get rid of another bucket, I can say get rid of 8, and I keep going. Now, there's a story here, which is this is actually, it's a very simple example of a situation where you see data as key value pairs, and you want to sample on the key only. Okay, in the simple example I gave you, the key was the whole thing. There was no associated value. The key was just the search query, and that's all we wanted to do. But you can. I'll give you a more complicated example in a minute. But the point is, you can hash the keys to buckets. You choose as your sample, you pick those keys that hash to the chosen bucket or one of the chosen buckets. And what this gives you is a sample in which either all or none of the elements that have a particular key value will appear in the sample. Okay. So let me just give you a more complicated example. I think this should be enough to make it clear. Okay, so my data, again, you can think of it as a set or a stream, it doesn't matter. But they're tuples that have an employee ID or name, the department to which they belong, and their salary. And the query I want is, I want to know what is the average range of salaries within a department. That is, for each department, there's someone getting the lowest salary in that department and somebody getting the highest salary. Take the highest minus the lowest. That's the range for that department, and I'd like to average that out over all departments. But again, I want to take a sample. I don't want to look at, maybe there are 1 million departments. I don't know what kind of a crazy organization this is. But I don't want to look at all 1 million departments. I just want to take a sample of the departments. But I want to do it sort of fairly. So I'm going to let the key be the department, and the value is the other fields, the employee and the salary. See, if I pick tuples at random, then let's say for the toy department, I'd get some of the employees and not others. And so if I computed the minimum and maximum salaries, what I would get is the minimum and maximum salaries for those employees in the toy department that happen to be in the sample. That would be a narrower range than the true range for the toy department. So I'd be biasing the ranges for the departments in some mysterious way. I know it's too small, but I don't know. There's no way for me to compute the correct value. Again, that's if I sample by position rather than by key. Okay, but the key is, if the key is the department, then I'm really just sampling departments, and that's really all there is to it, right? What I get is, for each department in my sample, I see all the employees in that department, and therefore can compute the exact range of salaries, and I can compute the average among all the departments that I've taken. And since I took the departments at random, there's a reasonable chance that the average in the sample is pretty close to the true average. Okay, at any rate, there's no bias.
Jeff?
Yes?
So, even in your previous example, it's clear that if you look at only the one bucket, one hash, you will find all the sort of unique queries there. But my question is about the remaining ones, because you would infer the ratio of say how many unique queries are based on how many remaining.
Yeah, right. Well, if I want to, okay. The fraction of unique queries should be the same in the sample and the set size, or the entire set should have 10 times, in this case, as many.
Right. But then, I'm not sure I understand is if we assume that the keys or the hashes of the arriving data, the queries might be, say, have a power law distribution, you might end up in a bucket which has a very popular key, and then you'll be over or underestimating the actual ratio. Is it that...
Well, there's no parallel. A hash function must be designed so that there's the power is zeroth power. It's equally likely to put in that case, a search query in any of the 10 buckets.
Yes. But say there is a unique query about, say, I don't know,
Yeah.
Bergendal Hotel. One.
Mhm.
And at the same time, there was a query for weather,
Mhm.
which was, 100,000 times.
Yeah. Well,
And then you would think it's 1 over 100,000, or while maybe this was a very...
no, because if the bucket only has two queries, weather and Bergendal, and Bergendal is unique and weather appears two or more times, you don't care how many more times it appears, you're going to say half the queries in this bucket are unique, and therefore I have no reason to believe other than that half of all queries are unique.
Okay, so you don't take into account the volume.
No, you're counting the fraction of queries that in the sample that are unique, just as you do in the full set, right? That is, I'm asking. Okay, actually, it actually doesn't matter. I mean, I assume that I was asking, among all the queries in the full set, how many of those queries appear only once. I could just as well ask, weighting queries by the number of occurrences. What is the weight of the queries that appear only once? I get a much smaller number. But if that's the query I want to ask, the sample still should be, well, the expected value will be the same because there'll be a few, queries like weather or porn is actually more common. But again, you'll, if a few really common queries happen to be in your sample, you get more variance. You increase, the variance goes up. So that's a little harder query to get the true result on. But it's the same principle. I mean,
My point was that since this variance will always be probably underestimating, because you will probably be in the bucket together.
I'm not. No, the expected value is true. Whether you're weighting queries by number of occurrences or not. But the variance is higher if you weight by number of occurrences because it does introduce more noise. But if that's the question you want to know, you got to ask it that way. Okay, let's see. I am. Let's see. Well, let's see how far we can go. Okay, this is again another story. Again, it's an old algorithm. I think it dates from around 1983, 4, something like that. And it's the problem is counting the number of distinct elements. Again, think of it as a stream. Okay, elements come in. Sometimes they repeat. Again, you can think of it as search queries if you want. This is sort of the dual of the problem that we were just talking about. How many different search queries are asked in a month? Okay. Well, you can solve the problem. All you have to do is keep a list of all the queries you've seen so far. And a new query comes in, you just look it up in some sort of a hash index or something, so you can do this fairly efficiently. You can see whether you've seen it or not. If you have seen it, you can ignore it. If you have never seen it, you have to add it to the set of things that you've seen. Okay. So just to give you a few examples of how this can be used, suppose I'm crawling the web. I might, when I reach a site, I might want to know whether or not this is a site that has been set up as some sort of a fake. And we're going to talk, I guess, tomorrow about combating link spam and how link spammers will set up sites of fake pages. Well, and what's an easy way to set up a site with 1 million fake pages? Just take some page from somewhere and duplicate it 1 million times. If you do that, the number of different words on that site is going to be really small, right? Because every word that appears will appear at least 1 million times. Or another way to do it is to just sort of produce random words and fill up your pages with random words. If you do that, you're going to get a lot more different words in that site than you would normally expect. And so as we're crawling a site, we might want to count the number of distinct words just to see, is this a spam site or not? Well, very common query. Facebook wants to report how many unique users visited. Okay, so think of the stream is every time you log on to Facebook, that's an element of the stream. If you log on 100 times in a month, they're only supposed to count you once. Okay, but you think, there are 1 billion users who might log on in a month, and so they've got to keep a set of 1 billion people that they've seen. Okay, not that you can't do it, but it's a pain in the neck. Another application which I've seen is, again, this has to do with web crawling again. Again, you can't crawl everywhere. So what you'd like to do if you come to a page is you'd like to decide, do I want to follow its links? Well, the answer is, if its page rank is going to be high, then yeah, you'd like to follow it. But if the page rank is low, it's probably not going to be the answer to anybody's search query anyway, so we'll just forget about it. Trouble is, you can't compute page rank until you crawled the web. You're just crawling the web now, so you don't know what the page rank is. But on the other hand, what you can do at least is compute the number of links to each page that you've seen. So if the number of links into a page is high, that's a good reason to suspect that the page rank will be high. It's not a guarantee, but it's reasonable. Okay, so suppose we don't really want to, for any of a number of reasons, including space, we don't want to actually store how many elements are we don't want to store the complete list of elements that we've seen so far. So what you want to do, the next best thing is we're going to estimate the count, and we want to do it in an unbiased way. So we'll say, okay, it could be an error up or down, but we'd like to know at least that the more effort we apply to estimating this count, the closer to correct we will probably come. Okay, so, and remember, little n is the number of elements that might exist. That's sort of the universal set of elements. Okay, now I want to just I'm going to take a hash function that maps elements to at least log n bits. It could be more. And for each element, I want to compute what I think of as the tail of the hash value. Okay, so we're going to let R of A is the number of zeros at the end of the bit string H of A. Okay, so again, assuming that H is going to give you a random bit string, half of them R of A is 0. Another quarter R of A is 1. An eighth R of A will be 2, and so on. And now I'm going to record the maximum R that I've actually seen. And my estimate based on this hash function will be 2 to the R. Okay, and sort of intuitively, if I see 2 to the R things, 2 to the capital R things, then it's probable that one of those things will have a tail as long as the logarithm of the number of things I've seen. That's capital R. Okay. Well, okay, it's not actually that simple, but let me first tell you why it works, then I'll tell you why it doesn't actually work. Okay. I mean, what is true is that you're going to be the value of capital R, or of 2 to the capital R, will be always near the number of elements, of distinct elements that you've seen. Okay, so look at it this way. What it says here is, the probability that some random bit string h of a ends in at least I zeros is 2 to the minus I. Okay, that is, it's certain, the probability is 1 that it ends in at least no zeros. The probability is a half that it ends in at least 1 zero, at least it's a quarter that it ends in at least 2 zeros, and so on. Now suppose that the true number is, the true number of different elements is m. Okay. Now, again, that means I'm hashing m different elements. So what is the probability that R is at least I? Well, okay, I claim it's this formula. Well, you can read the formula. But 1 minus 2 to the minus I is the probability that a given h of a doesn't have a tail of I or more zeros. Okay. And then if you raise that to the mth power, and this is sort of like throwing darts at targets again, the probability that all of the m different hash values have fewer than I zeros is that raised to the mth power. And, well, okay. And therefore the probability that R is at least I, that is, at least one of the m elements has a tail as long as I, will be 1 minus that. Okay. So here's our formula. The probability, again, 1 minus 2 to the minus I, all raised to the m. That's the probability that cap R is at least I. I'm sorry, the 2 to the R is at least I. Okay, now, I said 2 to the minus I is small. Assuming I is, is even a small, it's 3 or 4. 2 to the minus I is already kind of small. And I'm not going to go into this, but this is, again, sort of, it's, as with the darts and targets, you can write this as an exponent of E, and it turns out to be 1 minus e to the minus m times 2 to the minus I. Now, suppose 2 to the I is much bigger than m. That says R just was freakishly large, much larger than you would expect. Okay. Well, if 2 to the I is much bigger than m, then m times 2 to the minus I is e to the, it's e to a tiny fraction. And if it's a tiny fraction, I can replace e to the tiny fraction by the first 2 terms of the Taylor expansion. So I get, you can see what I've got there. And then the ones cancel. And what I have is m divided by 2 to the I. And then I just told you that 2 to the I is much bigger than m, so this is approximately 0. So that says the chances that you're going to get a way too big R is very small. On the other hand, if 2 to the I is much less than m, that is, are you going to get if I is much smaller than you'd expect, then e to the minus m times 2 to the minus I, that's e to a large number, and that's essentially 0, so it's 1 minus 0 is approximately 1. So this sort of says you always get close. Okay, that is the estimate will always be around m. Okay, but here's sort of why it doesn't work. Okay, and the intuition is, yeah, you're always around, 2 to the r is always around m, but when it's much bigger, when r is bigger than it should be, the value goes up exponentially. When it's much smaller, the values just decay a little bit. So there's this bias to the upside. Okay, that is, if you replace r by r plus 1, then it is true the probability that r is that big goes down by a factor of 2, but the value doubles. So when you sum all the possible values of capital R, you get an infinite sum. So what we want to do, what we really want to do is have a break, which we will in a second. Okay. What you're going to do, first of all, you're not going to just, I've been talking all along as if you only did one hash function. You actually have to do many hash functions, say, again, 100 different hash functions. And then you combine, each hash function will give you an estimate of the number of distinct elements, which will be 2 to its r, its capital R. And then you have to combine them. Well, average is no good because, again, because the infinite expected value, if I have one of those 100 values is just outsized large, it will bias the whole average. You could take medians, but since every estimate is a power of 2, what that says is you could only get powers of 2 as estimates. Again, you'll tend to be very close to, the median will tend to be very close to the true value, but it could be off by a factor of 2 almost. So what you do is you take your samples, you partition them into small groups of roughly log n in each group. You take the average within groups. Okay, so again, if a group happens to have an outsized large element, it will just give you a way too large average. But that's okay, because then you're going to take the median of the averages. And the chances of a lot of groups having very, very annoyingly large elements is small enough that it won't affect the median. Okay, so you take the median of the averages and you're okay. Okay, and now I think this is probably a good time to take a break, and we will continue. I get the feeling I will probably not be able to get through slide set 5 today, but that's okay because 7 and 8 are kind of small, so we'll catch up tomorrow.